Alright, here's a shear moment diagram problem that I will do by the graphical or inspection method way and I will do it using the cut method so you can see both ways. So we have a fixed beam, fixed at A, distributed load, point load, and a moment. So everything except for a non-uniform distributed load, but this is a good one. So the first thing we have to do is find our reactions. So at A we have AY, we have AX, which we can see is 0, and we have a moment at A because this is fixed. So 3 reactions at A. Then to calculate those reactions, we're going to turn this distributed load into a point load just for that purpose. So it will be 40 kilonewtons per meter times the 3 meters it acts over, and it'll be 120 kilonewtons. So now we can do equilibrium to solve for reactions. So we have sum of the moments about A equals 0 equals the reaction moment at A, which is a positive MA, the way I have it drawn, minus the 120 kilonewtons that is acting half the distance since it's a uniform load, so 1.5 meters from A. 120 times 1.5 meters. Then we have this point load, so that would be plus 50 kilonewtons times 3 meters. And then the applied moment is in the negative direction, so we have minus 60 kilonewton meters. And we find out that the moment at A, the reaction moment, is a positive 90 kilonewton meters. Then we sum the forces in the y direction, that equals 0. It equals AY minus 120 kilonewtons plus 50 kilonewtons, and then the moment doesn't go into this equation. So we have AY equals 70 kilonewtons. So we could label those. This is 70 kilonewtons, and this is 90 kilonewton meters. All right, so next step is to draw a shear diagram. Shear diagram is related to the load diagram. So everywhere with a significant point on the load diagram, we're going to draw a line. This is not a significant point. It's an imaginary point that we use to calculate the reaction, so it doesn't really exist. What really exists is that distributed load. That didn't work. So the next important point is where the distributed load ends, and that point load is applied. And the last important point is the end of the beam where the applied moment is. Okay, so the shear diagram. So we draw our shear diagram with horizontal line, end of V, and the units are kilonewtons. And we look at what happens. And the first thing that happens is we have this reaction of 70 kilonewtons going up. So our shear diagram goes up by 70 kilonewtons. Then, as we walk across the beam, every meter we go, the shear is going to go down by 40 kilonewtons. So every meter, we have to take 40 kilonewtons away. So this distributed load is going to be a linearly decreasing load down to the total load is 120 kilonewtons. So 70 minus 120 is going to make us land at negative 50 kilonewtons. Now we cross 0, so that's going to be important for our moment diagram, but we'll worry about that in a minute. So now we're down at negative 50. Well, the next thing that happens is at this point, we jump up by 50. So now I'm going from 50 to 0. And then if I continue to walk across this beam, nothing happens. There's an applied moment, but that has nothing to do with our shear diagram. So the shear just stays at 0 for the last meter. Alright, so if we called this point 1, we would have V1 equals 70 kilonewtons. If we called this point 2, it would be V2 equals 70 kilonewtons minus 120. So that is, we could think of it as the area of the distributed load. So if it was a triangle, it would be half the base times the height. But it was a rectangle, so it was just, we can think of the height being the magnitude and the base being the length. And then that equals negative 50. And then we had our point load. So that would be 0.3 right here. A point load, V3, brings us from negative 50 plus 50 to 0, and then nothing else happens. So that's the rest of the beam. Okay, then it's very important that we calculate the x value where the shear is 0, because that will be an important point on our moment diagram. So calculate where x is 0. And we use similar triangles. So we're going to start with this triangle, and then we're going to make a triangle that looks like this. So it's kind of an imaginary triangle. Alright, so we're going to have the height of the first triangle is 70, and the distance is x. That's what we're solving for. So 70 over x equals the whole height of this triangle, which is 120, over the whole length, which is 3. And we find out that x equals 1.75 meters. So this is 1.75 meters. Okay, so we know that the value of the shear is the slope of the moment. So if the shear is 0, that means the slope of the moment is 0. So it'll be either a maximum or a minimum point. That's why we care. And we're going to have to calculate this area to find the moment. So we care for that reason too. Alright, so now we can calculate the moment diagram. So the moment has units of kilonewtons times meters. Okay, so we're going to calculate moment diagram using areas on shear diagram and moments. So we know that at A, it was fixed, and we had an a reaction moment that came out to this positive 90 kilonewton meters. It's positive, so that means on the moment diagram, we jump down 90 kilonewton meters. So this is negative 90. So M1, call this 1. M1 equals negative 90 kilonewton meters, and it jumps down because we have a positive moment there. Alright, so then to find out what the moment is at this point, we need to know the area of this section, because then we can take our current moment minus this area, and that will be the moment here. And this area is positive, so we will add it to our negative 90. So we'll calculate this first area, 1. So the area of 1, it's a triangle, so it's 1/2 times the height of 70 kilonewtons times the base of 1.75 meters. So it equals 61.25 kilonewton meters. So then to find M2, it equals negative 90 plus 61.25. And that is negative 28.75 kilonewtons meters. So now this is a straight line that's decreasing, so we're going to need a curved line here, and we need to figure out how it's concave, what concavity it has. So remember, the slope of the moment diagram equals the value of the shear. And the value of the shear is 70 here and 0 here. So the slope is going to be highest at the beginning, and it will be 0 at the end. So it will look something like this. And that value will be negative 28.75. All right, now we have a negative area for area 2, so we'll subtract that from this moment to find out what the moment is here. So now we'll calculate area 2. So A2 equals 1/2. The height is negative 50. The length is 3 minus 1.2 or 1.75, so it's 1.25. So this equals negative 31.25. So we add these two together. This is also kilonewton meters. And we get that this is M2 here. We get M3 equals negative 28.75 minus 31.25, and that equals negative 60 kilonewton meters. So now we're going back down, and again we look at the slope to tell us the concavity. So it's 0 here, bigger negative number here, so the slope is going to be negative but steeper as we get to 2. So now go something like that. Okay, now we have to pay attention to what's going on up here. So we know at the end we have this. Oh yeah, and we're at negative 60 at 0.3. Nothing happens as far as moment is concerned. There's no shear area here. So no shear area. So we go straight over. And then this is a negative moment. So that means we jump up by a positive 60 and we get to 0. So jump up because of negative 60 kilonewton moment. Alright, so that's our shear moment diagram. So remember to think about each point is the value. So V is the slope of M. So when the shear is larger, so large V, large slope, and here V equals 0, so slope equals 0. Hopefully that helps you keep track of that. Alright, so that's the graphical method. Now the cut method, same reactions, so they're all there. And what we're going to do is we have to cut it anywhere things change. So for this problem, we have to do 2 cuts. We need to cut it somewhere along the beam here, cut 1, and somewhere along the beam here, cut 2. All right. So cut 1, we're going to have an x that is 0 is less than or equal to x is less than or equal to 3 meters. Okay, so here we are going to have okay. So now we're going to cut it and look to the right for this first cut. So I'm going to draw this, and the distance along this is x, and then we have our 70 kilonewton reaction, and we have our 90 kilonewton meter moment, and then we have this distributed load of 40 kilonewtons per meter, which, since we're solving for reactions, internal reactions now, I'm going to call this 40 times x, and the distance it acts is x over 2 on either side. Alright, and then using the proper positive sign convention, when I'm looking at the left side of the beam, shear is going down. This would be shear 1 for section 1, and moment is going in the positive direction. Alright, so we have to solve for V1 and M1. Those are the two things we don't know. So we have sum of the forces in the y equals 0 equals a positive 70 kilonewtons minus 40 times x. So this is an equation for x along this section of the beam. This is an equation for this section of the beam. Alright, so we have 70 kilonewtons minus 40x, and then we have to subtract the v that we're solving for, and we get v, if we rearrange this, equals negative 40x plus 70. So this looks just like y equals m, the slope, times x plus b, the y-intercept, which, if we look here, and so we have the y-intercept was 70, the slope is the value of the distributed load, 40 kilonewtons per meter. So that's important. The slope, m, equals w, the distributed load. Okay, so then we can take sum of the moments about the cut. It equals 0. It equals m1 minus 40 times x. The distance away is x over 2 times, that's a positive, a negative 70 times the full x plus 90. We solve for m1. We get negative 20 x squared plus 70 x minus 90. Alright, and then you can plot that in your calculator or wherever and see that it matches this section of the moment diagram. Alright, so now we need to do our second cut. This cut 2. We're going to look at it from the right. So for cut 2, we have 3 is less than or equal to x is less than or equal to 4. So the last meter of the beam. So here we have our beam. And we have an applied moment, the negative direction of 60 kilonewton meters. Then positive sign convention. This is V2 going up, and the moment is going to be negative M2. And the hardest part about cutting it and looking at the right side is knowing the distance. So this distance is the total distance of the beam 4 minus x. That's this distance. Okay, but this one's kind of easy, so you don't get to see how much fun it is to work with that. So now we can sum forces in the y equals 0, and the only thing we have is V2, so that equals 0, and that tracks with our shear diagram. Shear equals 0, and then the next thing we have is sum of the moments about the cut equals 0, so we have negative M2 equals, minus 60 kilonewton meters, so we get that M2 equals negative 60 kilonewton meters. And that's the equation, and if we look, that's the equation of that line. So there you go.